Welcome to this lecture series in coordinate geometry about straight lines. Uh, in this lecture, we will look at how to find the coordinates of the incenter of a triangle. And the main ingredient that we will need is the section formula, which says that if suppose we have a line segment whose endpoints have these coordinates x1, y1 and x2, y2, and there is a point P which divides this line segment in the ratio a is to b, then what are the coordinates of P? So the coordinates of P are given by this formula, bx1 plus ax2 divided by a plus b, comma by1 plus ay2 divided by a plus b. So that's a nice formula. Here are some problems for practice. And now let us get started. So I want to make this self-contained, and hence I will be going through all the basics. So first we need the notion of the angle bisector of an angle. Suppose we have an angle BAC given to us. Then the angle bisector of BAC is a line passing through A, let's call it AD, such that angle BAD is equal to angle CAD. So such a thing is called the angle bisector of a given angle. And it's a line, so it goes both ways, but okay, I don't want to spend too much time on this. Okay, so here is the important property of an angle bisector. So a point M, so again we have this angle BAC, then a point M lies on the angle bisector of this angle BAC if and only if M is equidistant from the two lines AB and AC, rather two line segments AB and AC. Okay, so I mean this is just an application of congruency. Basically, if you have a point M on the angle bisector, then you drop these perpendiculars and call it P, call it P, call it Q. Then you just show that these two triangles are congruent by using angle-angle side congruency, and then it'll follow that MP is equal to MQ, and you can just reverse this reasoning to obtain the other direction of this fact. So I leave you to fill the details. I'm sure you have learned this in your some geometry class at some point. So this is an interesting theorem, the angle bisector theorem as we call it. So it says that suppose we have a triangle ABC and we draw the angle bisector through the vertex A. So it's the angle bisector of this angle BAC. So the theorem says that the ratio AB upon AC is same as the ratio BD upon DC. So that's very interesting. And let me give a proof. I'm sure you learned this at some point, but here is how we prove it. So what we will do is first we will draw a line parallel to this angle bisector passing through C. So here is that construction. So we draw that line, right? So the orange lines are parallel, and we extend AB to meet the newly constructed parallel line. So okay, so let's say they meet at I don't know, let's call it B prime maybe. So they meet there, and now if this angle is suppose this angle is X, then what is this angle? This angle is also X because these two, this angle and that angle are the same because this was the angle bisector. So this is also X. And now what is that angle? So the orange lines are parallel, and hence corresponding angles or whatever is the name, this becomes also X. Basically, I'm saying that this angle is same as that angle. So we have that. And again, by the fact that orange lines are parallel, this is X implies this is also X. So that is X. And therefore, this is an isosceles triangle because these two angles are equal. So we deduce that AB prime is equal to AC. So maybe I should have called it C prime. That's a better name. So AC prime is equal to AC. Okay. And now by the fact that again the orange lines are parallel, we see that triangle ABD is similar to triangle BC prime C, and therefore AB upon, or let me not write AB, let me say BA upon AC prime, this is equal to BD upon DC. So this upon that is equal to this upon that. This is by the similarity of these two triangles. And as we noted, AC prime is same as AC. AC prime is same as AC. So yeah, this is that and this is that. So we have proven what we said. So this is the angle bisector theorem, and now we can, yeah, so now we have to do one more thing. We have to define the incenter, and the main fact to notice is the following, that if you have a triangle, then the angle bisectors of the three angles are concurrent, meaning that the three lines meet at a common point. Okay, so this is very easy. Suppose we have drawn two angle bisectors. So we want to say that this point I, the point of intersection, is the point with the property that it is equidistant from the three sides. So fine, how do we show that? Let's maybe, so drop a perpendicular from I to this thing, drop a perpendicular from I to that side, drop a perpendicular to this side. And now by the fact, the property of the angle bisector that we discussed, since this is an angle bisector of this angle, these two things have the same length. So we will mark that. And now since this is an angle bisector, or the angle bisector of this angle, we see that these two have the same length. Hence that is the case. And therefore if we join, so if we join C with I, since I is a point equidistant from these two line segments, this has to be the angle bisector of this angle. That's the property, that's the property of the angle bisector that we discussed. So this is also the angle bisector. So the three angle bisectors meet at a common point, and that point is the special point with the property that it is equidistant from the three sides of the triangle. And this is called the incenter. I is called the incenter of triangle ABC. Right. So now we can write down the coordinates of the incenter. So to write down those coordinates, first we will use a shorthand. So the length of BC we will denote as little a. Length of AB will be denoted as little c, and length of AC is little b. So of course we can express a, b, and c, in terms of these coordinates, because a is nothing but what is given by the distance formula. It is x2 minus x3 whole square plus y2 minus y3 whole square, and then the square root of this thing. So which is why this is a nice shorthand, because that's a horrible expression that we do not want to repeat all the time. Okay, so we need to find the coordinates of I. First we will find the coordinates of D. But we know by the angle bisector theorem, BD is to DC is what? Is this is to that, which is C is to B. So D divides BC in this ratio, C is to B. And hence the coordinates of D by the section formula are, so this is C, this is D, so C is to D, and hence the coordinates are cx3 plus dx2, sorry, this is not D, this is B, bx2, there is no D, B plus C, comma, similarly for the y coordinate. So these are the coordinates of the point D. And now let me erase this one. We don't need that. So now we want to find the coordinates of I, and forget everything. Just consider this triangle. This is the triangle that we want to work with. Here we have an angle. We have the angle bisector of this angle. So by the angle bisector theorem applied to this triangle, we know that di upon IA is dB upon AB. So AB is written as C, and we know the formula of it in terms of these 2 points. But what about BD? We can also write down BD. So BD is what? BD is, how do we find BD in terms of A, B, and C? This this upon that is C is to B, and hence BD is nothing but C upon B plus C times A, or maybe I should first write BC, right? Since this upon that is C is to B, the fraction of the length that this consumes is C upon C plus B of the total length, and the total length is A. That's the notation. So that's what BD is, and therefore DI is to IA is equal to this thing, CA upon B plus C is to C, right? This is by the angle bisector theorem, because the length of this is this much and the length of that is that much. Okay, which is nothing but, maybe this helps computation, this is nothing but A upon B plus C is to 1, right? So the coordinates of I, now we apply the section formula to this thing. So the coordinates of I would then be A upon B plus C times x1 plus C x3 plus B x2 upon B plus C divided by A upon B plus C plus 1. And similarly for the y coordinate, so that I will write later. So if we compute this, what do we get? If we compute this is same as ax1 plus bx2 plus cx3 upon a plus b plus c, and similarly the y coordinate would be ay1 plus by2 plus cy3 divided by a plus b plus c. So those are the coordinates of the in-center, and if you expand the expression for a, b, and c out, it will be an impossible thing to handle, and which is why we have used this notation. But you see, if we knew numerically what is x1, x2, y1, y2, x1, y1, this was supposed to be y1, I'm sorry about that. Yeah, so x1, y1, x2, y2, x3, y3, if we knew all of these three things numerically, then we can compute a, b, and c, and then we can also compute the in-center completely. So that's that's the end of this lecture. As usual, like, comment, share, subscribe, and I'll see you next time.